In the beginning, there was no sun and no radiant disk blazing at the center of space. There was no warmth and no dawn. There was only a drifting wilderness of cosmic dust and a vast molecular cloud stretching across light years. Inside this silent cloud lived ancient grains that had traveled through interstellar space for ages beyond imagination. These grains carried the memory of older stars and older explosions. They were fragments of cosmic furnaces that had died long before the future sun was born. This cloud was dark and cold, yet held the seeds of everything that would one day become our solar system. This region is known as a stellar nursery, yet this nursery was far from empty. It was seeded with materials older than the star it would eventually create. The temperature inside was so low that atoms moved slowly, yet even in that frozen darkness, the ingredients of future worlds drifted freely. Carbon grains, metal flecks, ice crystals, and silicate fragments floated like ghost embers from forgotten fires. Many of these grains had been born in the outflows of ancient red giant stars. Others were forged inside supernova detonations that had taken place millions of years before this cloud began to collapse. These relics are known today as pre-solar grains, and they're preserved inside some of the most primitive asteroids. They reveal a truth both astonishing and profound. Not everything in our solar system was made by the sun. Some things are far older, built in distant stars scattered across the Milky Way. Gravity began whispering through the cloud, drawing scattered dust into slow spirals. The cloud grew denser in certain regions, and small ripples expanded into larger waves. Matter clumped together, and these pockets of density became the earliest seeds of the solar system. The central region of the cloud was still faint and cold, yet pressure was slowly building toward the moment when a new star would ignite. Meanwhile, the ancient grains drifted freely, mixing and softly colliding. They gathered into tiny clusters. These clusters would one day become the first solid bodies of the solar system. They were the early planetesimals. They were only a few miles across, yet destined to become the foundations of asteroids, planets, and comets. The interstellar cloud drifted through the Milky Way, shaped by galactic tides, supernova shock waves, and cosmic turbulence. Each disturbance added new layers of ancient dust to the collapsing region, enriching it with the remnants of long-dead stars. Then a powerful shock wave arrived, possibly from a supernova explosion nearby. This wave pressed into the cloud and triggered a rapid collapse. Material spanning light years began moving inward toward what would become the heart of the solar system. This collapse marked the true beginning of the story of our sun and its ancient asteroids. Through all this pressure, the pre-solar grains remained mostly untouched. They survived the fall and carried within them the story of cosmic eras much older than our future star. As the cloud collapsed, it began to spin faster, just like an ice skater pulling in her arms. The spinning cloud flattened into a giant, rotating disk known as a protostellar disk. It stretched across billions of miles and was filled with gas, dust, and ancient material. At its center, the young protostar began to form, yet most of the disk remained cold and dark. Heat had not yet reached the outer regions where the earliest asteroids would begin to emerge. Before the sun ignited and before planets arose, the oldest future asteroids started forming in these dark, distant regions of the disk. They were composed of the untouched pre-solar grains. As they grew layer by layer, they locked those ancient materials deep within themselves. These primitive asteroids became time capsules holding pieces of stars that died long before a solar system was born. They would preserve these relics from heat, from radiation, and from transformation. They would become messengers from a time before the sun. Thus, the earliest asteroids were born as cosmic museums carrying the history of forgotten stars. Over the next chapters, we will explore their origins, their chemistry, their role in planetary creation, and the extraordinary fact that some asteroids are indeed older than the sun itself. But for now, the story remains in darkness. A silent cloud waits to ignite. A universe prepares to rise from ancient dust, and the oldest materials continue drifting quietly through the womb of the future solar system. The collapse of the molecular cloud turned the quiet, dark cradle of dust into a realm of rising motion. Gravity tightened its grip with every passing moment, and the once slow, drifting particles now accelerated toward the forming center. In this phase, the protostellar disk grew wider, flatter, and more defined. The newborn structure resembled a colossal whirlpool made of dust gas and fragments older than any future planet. Although the center of the disk was heating steadily, the outer regions remained cold and silent. This temperature difference would become one of the most important forces in shaping the earliest asteroids. In the frozen outskirts of the disk, the ancient grains stayed stable and unchanged. They did not melt and they did not vaporize. They held their original identity from a time before the sun existed. Here, the earliest solid bodies began to grow through a process called accretion. Tiny grains struck each other gently at first, and their surfaces stuck together through electrostatic attraction. Over time, these clumps grew larger and heavier. They evolved from microscopic particles into centimeter-sized pebbles. Pebbles merged into stones, and stones merged into boulders. These boulders became kilometer-wide bodies that astronomers today call planetesimals. As these planetesimals drifted through the disk, they collided often. Some merged peacefully. Others shattered violently and created new clouds of fragments that would join with other bodies. This chaotic ballet defined the earliest era of solid formation in the solar system. Yet the most primitive planetesimals, those formed in the cold zones, still protected the presolar grains locked inside. This made them different from planetesimals born closer to the warming center, where heat altered the minerals and erased the ancient record. During this period, the sun was still not a star. It was a growing protostar surrounded by swirling material. It pulsed softly, releasing jets of energy along its magnetic poles. These jets carved tunnels through the surrounding cloud and shaped the disk further. The inner region became hotter and more turbulent. Minerals here began to melt and reform. This is where the earliest molten droplets, known as chondrules, were born. They formed through brief, intense heating events and cooled rapidly into spherical grains now found in many meteorites. Yet in the cold outer disk, the presolar grains survived unchanged, and these grains entered the bodies that would later become the oldest asteroids. While all this happened, the disk continued to rotate. With each rotation, particles sorted themselves by weight and temperature. Heavy elements sank toward the midplane of the disk, while lighter gases hovered above. This layering allowed rocky bodies to accumulate more easily along the midplane. The cold regions beyond the frost line, the boundary where water could freeze, allowed ice-rich bodies to form. Some of these icy planetesimals would become comets. Others would become carbon-rich asteroids. These carbon-rich asteroids are the ones that hold the highest concentration of presolar materials. They're the cosmic libraries that tell the story of stars older than the sun. Farther inward, the forming sun continued to grow hotter as gravity squeezed it with increasing strength. Yet the protostar was not ready to ignite. It was still gathering mass from the surrounding disk. Streams of gas spiraled inward, feeding the young star and adding energy to its hidden core. The moment of ignition was approaching, yet the primordial asteroids were already forming before this event. This means they are among the oldest solid objects in the entire solar system. Some even contain materials from before the solar system existed at all. In this ancient environment, the planetesimals interacted through gravity. Some captured smaller objects. Others were pulled into new orbits. The gravitational presence of larger growing bodies shaped the pathways of the smaller ones. In some regions, planetesimals clustered and began forming early protoplanets. But in other regions, particularly in the zone between Mars and Jupiter, the formation of large planets was disrupted. This disruption would eventually allow the asteroid belt to form a region of countless bodies, many of which preserve the oldest unchanged material. The cause of this disruption was the rise of a giant. Jupiter, the future king of planets, was beginning to take shape. Its enormous mass exerted powerful gravitational forces across the disk. These forces prevented the small bodies in the middle regions from merging into a full planet. Instead, they broke apart, regrouped, and spread into a broad belt of debris. This belt would become the home of the oldest asteroids, including those containing presolar grains. Jupiter became both a guardian and a destroyer. It prevented planetary formation in this region, yet it preserved the ancient objects by protecting them from drifting toward the sun, where heat would have erased their ancient signatures. By the end of this stage, the foundation of the solar system had taken shape. A protostar burned softly at the center. A massive disk rotated around it. Early comets, icy worlds, planetesimals, and primitive asteroids drifted through the spinning expanse. And hidden inside, the carbon-rich bodies were the relics of stars that had died before the sun even formed. These ancient grains waited silently for billions of years until one day pieces of these asteroids would fall to Earth and reveal their story to us. As the young protostar grew heavier, the pressure in its core climbed toward a threshold that would change the destiny of everything around it. For millions of years, gravity compressed the central mass tighter and tighter until the atoms inside were forced into close contact. Heat rose from this pressure, and light slowly began leaking from the surface of the forming star. This glow was faint at first, yet it signaled an important shift. The frozen stillness of the early disk was ending, and a new era of rising heat was beginning. For the ancient presolar grains locked inside primitive planetesimals, this was a moment of danger, for most material in the solar nebula was about to be scorched, reshaped, or vaporized. Yet the bodies that lived far from the center remained cold enough to preserve their ancient memories. Deep inside the core of the protostar, hydrogen atoms were being squeezed with such force that they began fusing into helium. This nuclear fusion released immense energy. With this ignition, the protostar became the sun. It was now a true star, shining with steady power and radiating strong heat across the disk. The moment of ignition sent a powerful surge of energy outward. This early solar wind swept through the surrounding nebula like a storm of light and charged particles. It pushed away much of the remaining gas and thinned the disk dramatically. The inner solar system was blasted clean, while the outer regions experienced a gentler effect. This violent cleansing marked the end of the sun's birth and the beginning of a new stage in the evolution of asteroids. In the inner region, the rising heat melted and altered nearly every solid grain. Minerals vaporized, recondensed, and fused into new structures. Rocky bodies near the young sun underwent extensive transformation. They lost almost all traces of presolar grains because the heat erased their original features. Their minerals recrystallized into new forms shaped entirely by the newborn sun. This is why the oldest presolar fingerprints do not appear in most inner solar system rocks. Instead, these ancient signatures survived only in the cold regions where heat never reached. The outer disk remained a sanctuary. Temperatures there were low enough that ancient grains remained unchanged. The planetesimals drifting in this zone acted like cold storage vaults. They absorbed grains from earlier generations of stars and held them deep within their interiors. Carbon-rich asteroids in particular became the greatest preservers of presolar material. They contained organic compounds, volatile elements, and microscopic crystals shaped in other star systems. These asteroids would one day become the key to understanding that some of the matter in our solar system came from distant corners of the galaxy. As the sun matured, its intense radiation influenced the disk in new ways. It created pressure gradients that pushed small dust grains outward. This movement helped enrich the outer regions with fine materials from the inner disk. While this flow brought new components to the cold zone, it did not erase the older grains. Instead, it increased the diversity of the growing asteroids. Ancient dust from before the sun mixed with newly heated dust from inside the disk. These layers combined to form the complex textures we find today inside carbonaceous chondrites, which are some of the most primitive meteorites ever discovered. The gravitational landscape continued to shift during this era. Growing planets, pulled on the small bodies around them. The large mass of Jupiter disrupted orbits across the forming asteroid belt. Many planetesimals collided and shattered. Others merged into sturdier bodies. This chaotic cycle of creation and destruction shaped the distribution of asteroids. Those that survived became fragments from a time older than the planets themselves. They drifted quietly through the belt, carrying ancient dust grains that had never been touched by the sun's heat. Meanwhile, the outermost regions of the disk remained largely untouched by violent collisions. Here, icy planetesimals formed the earliest comets. Like the primitive asteroids, these comets preserved pre-solar grains. Their interiors remained frozen for billions of years. When modern spacecraft sampled these comets, they discovered materials older than the sun, just as meteorites had revealed. This confirmed that the early solar system was not a single birthplace of matter. It was a collector's realm, a mixing ground for dust from countless stars across the galaxy. As millions of years passed, the disk continued to thin. Gas flowed inward or was blown away. Dust settled or was consumed by growing planets. The solar system entered a more stable phase. The planets took shape. The asteroid belt formed. The sun blazed with steady power. Yet hidden inside many of these small rocky bodies were pre-solar grains waiting for future discovery. They had survived collapse, heat radiation, and violent collisions. They had outlived entire stellar lifetimes and cosmic catastrophes. Now they drifted in the cold belt between Mars and Jupiter, carrying stories written before our sun was even born. By the end of this era, the solar system had become recognizable. The sun shone at the center. The planets orbited in young paths. Comets and asteroids traced ancient routes through the cold regions. The oldest asteroids containing pre-solar grains remained untouched by geological activity. They did not melt. They did not differentiate. They preserved the oldest secrets of cosmic history. These asteroids are not just remnants of the early solar system. They are relics from before the solar system existed at all. As the young solar system settled into shape, a new era began, an era defined not by gentle drifting, dust, but by violent encounters. The calm glow of the newborn sun illuminated a realm filled with thousands of rocky bodies spinning through space at great speeds. Some were the size of mountains, others were merely boulders, yet all of them were crossing paths inside a still unstable system. The gravitational pull of the forming planets, especially the rising giant Jupiter, shook the asteroid belt into a storm of movement. Orbits shifted repeatedly, and collisions became inevitable. This era is known by planetary scientists as the time of heavy bombardment, and it was during this age that the oldest asteroids faced their greatest test of survival. The asteroid belt in this early epoch was far more crowded than it is today. Countless planetesimals attempted to pull together into a large planet, but Jupiter's massive gravity tore their progress apart. Instead of forming a world, they crashed into one another, sending fragments across the belt and beyond. Many primitive bodies were completely shattered, yet others endured these violent impacts. The ones that survived are the ones that interest scientists today, for they sheltered the earliest untouched pre-solar grains. These ancient asteroids did not melt, and they did not undergo internal heating. They remained primitive and cold, preserving the original ingredients of the pre-solar cloud. The collisions themselves played a major role in shaping the composition of the asteroid belt. Some impacts were so strong that they exposed the inner layers of planetesimals and scattered material across millions of miles. Other impacts were weaker and created rubble pile asteroids, loose collections of fragments held together only by gravity. These rubble pile bodies often contained a mixture of materials from several different parent bodies. They carried both ancient pre-solar grains and newly formed minerals created during the heating events near the young sun. Such asteroids became rich libraries of diverse cosmic history. During this chaotic age, dust clouds created by impacts drifted through space and coated other bodies. These clouds carried both old and new materials. When they settled onto the surfaces of other asteroids, they added further layers to their structure. Over time, this layering created complex geological textures inside many primitive asteroids. Some regions held grains older than the sun. Other regions held minerals formed after the sun ignited. This mixture turned each asteroid into a timeline of cosmic events preserved in stone. The gravitational forces of the planets also caused many bodies to migrate inward or outward. Some are pulled toward the inner solar system, where heat from the sun altered or destroyed their ancient materials. Others were pushed outward into colder realms where their interiors remained frozen. The ones that were forced inward often lost their pre-solar grains because rising temperatures transformed their minerals. But the ones that stayed in the cold outer zones continued to protect their ancient material. This is why carbon-rich asteroids located in the middle and outer regions of the belt are the most valuable for understanding pre-solar history. Meanwhile, the outermost regions of the solar system experience their own collisions, though at a slower pace. Icy planetesimals smashed into each other, producing comets with fractured cores and layered structures. Many of these icy bodies also preserved pre-solar grains deep within their frozen interiors. Comets therefore became distant cousins of the ancient asteroids, sharing a similar ability to store material from before the sun's birth. When modern spacecraft visited these comets, they found grains that matched the chemical fingerprints of pre-solar materials discovered in meteorites. As millions of years passed, the collisions slowly decreased. The solar system was clearing itself. Bodies that were unstable were destroyed. Bodies that were stable settled into long-term orbits. The asteroid belt thinned and fewer objects remained. The survivors were those that could endure repeated impacts without melting. These survivors are the same bodies that today fall onto Earth as meteorites. When scientists analyzed their structure, they discovered the tiny grains that proved some materials inside the solar system are older than the sun. The surviving primitive asteroids became guardians of the pre-solar story. They carried within them the minerals that had formed in ancient red giants and exploded in supernova blasts. These grains were older than every planet and older than the sun itself. They had drifted through interstellar space for uncounted ages until the collapsing cloud gathered them into the early solar system. They passed through the chaos of bombardment without being erased. They endured pressure collisions and radiation. They survived everything the young solar system threw at them. By the end of this violent era, the solar system reached a new level of stability. The great bombardment faded. The planets followed stable paths. The asteroid belt settled into its familiar form between Mars and Jupiter. Many rubble piles drifted peacefully. Many intact bodies rotated slowly under the sunlight of a star that had once been dark. Yet inside many of these quiet asteroids slept the oldest solid material in the solar system and beyond. These bodies were no longer simply rocks. They had become time-traveling messengers carrying within them stories from before the birth of our sun. When the era of heavy bombardment faded, the surviving asteroids drifted quietly in their orbits, yet their calm appearance concealed the ancient stories trapped within their rocky hearts. Over billions of years, small fragments broke off these bodies through gentle collisions or thermal cracking, and some of these fragments eventually found pathways toward the inner solar system. They traveled for millions of years until gravity pulled them toward Earth. Other grains came from supernova explosions where intense heat and pressure forged rare isotopes. Still others came from ancient dwarf stars or fast-dying stellar remnants. These grains are incredibly tiny, often only a few microns across, yet they hold the entire chemical memory of their parent stars. They're like fossils, but instead of bones, they preserve the last breaths of ancient suns. The meteorites that contain these grains are extremely valuable to science. They provide the only direct physical samples of material formed outside our solar system. Every grain is a messenger from a different corner of the galaxy. When scientists study them, they are studying stars that lived and died billions of years before Earth formed. These grains give us a way to explore stellar evolution without leaving our planet. They allow us to observe the products of nuclear fusion in other stars. They allow us to trace the journey of atoms through galactic time. Inside a single carbonaceous chondrite, meteorite scientists can find a mixture of materials that formed in different epochs. Some grains are older than the Sun. Some grains formed in the early solar nebula during brief heating events. Others formed during the violent collisions of the early asteroid belt. This variety makes each meteorite a layered record of cosmic history. When researchers slice open these stones, they read them like chapters in a book. One region tells the story of interstellar dust. Another region tells the story of the solar nebula. Another region tells the story of early collisions. The complete meteorite contains billions of years of history embedded in its minerals. As scientists refine their techniques, they develop tools that could isolate individual grains and analyze their isotopic makeup. These tools revealed stunning details. Some presolar grains turn out to be older than 5 billion years. Others showed patterns that match stars in late stages of nuclear burning. Some grains came from slow, cooling red giants. Others came from fast, explosive events. Each grain had a unique story, and together they formed a map of the processes that shaped the galaxy long before the solar system existed. One of the most remarkable discoveries was that presolar grains were incredibly resilient. Despite drifting through interstellar space, surviving the collapse of the solar nebula, enduring collisions, and eventually landing on Earth, they preserved their original form. Their crystalline structure remained intact. Their isotopic fingerprints remained untouched. This resilience shows how stable these grains are and why they could survive the birth of the Sun without losing their identity. They are among the oldest surviving solids in the galaxy, and they provide a direct link to the history of the universe. Meteorites also revealed organic molecules, some simple and some complex. These molecules also formed in the cold outer regions of the early solar nebula and in interstellar clouds. They were preserved inside the same primitive asteroids that carried presolar grains. Their presence suggests that the building blocks of life were widespread across the galaxy long before Earth formed. These organic molecules traveled through space for ages until they arrived on the young Earth through meteorite falls. This suggests that life's ingredients may have been delivered to our planet by ancient asteroids that preserved both chemical and stellar history. Through meteorite analysis, scientists gained a deeper understanding of how the earliest asteroids formed and how they preserved the materials that came before them. Each primitive meteorite that falls to Earth strengthens the idea that our solar system did not form from pure local material. Instead, it formed from a mixture of cosmic debris that had traveled great distances and lived many lives. The first asteroids absorbed this ancient dust and protected it within their cold interiors. Billions of years later, they brought these ancient grains to Earth, giving us a direct look at the time before the Sun existed. By the end of this chapter, the role of meteorites becomes clear. They're not simply stones that fall from the sky. They are archives. They are time capsules. They hold the oldest solid materials we have ever touched. They connect us to stars that died before our Sun was born. They show that the story of our solar system began long before the Sun ignited. Through them, we learned that the matter inside our world once belonged to many other worlds across the galaxy. The early solar region was still an unsettled cradle of matter and energy, and the oldest asteroids moved through that region like quiet witnesses of change. Their surfaces held the marks of countless encounters with light heat and drifting dust, and every mark preserved a moment from an era far older than the Sun. These bodies had cooled long before the Sun ever burned bright, which meant their rocky layers held a silent record of temperature patterns, magnetic behavior, and radiation conditions that existed in the earliest cosmic environment. They were not just stones wandering through space. They were pages from the first book of our local universe, and each page carried the truth of what existed long before the dawn we recognize as the birth of our star. When the Sun finally awakened and began shaping the space around it, the oldest asteroids were forced into new motions, yet they did not lose their original identity. They now carried two eras within them, the age before the Sun and the age after the Sun. This rare dual identity made them some of the most significant relics in the entire solar family, because they linked two cosmic chapters that no other object could connect with such clarity. Their minerals spoke of conditions older than solar heat, and their altered surfaces spoke of the moment when solar light finally arrived and washed over the ancient darkness. Inside these ancient asteroid, scientists found minerals that formed under slow, cooling far away from strong gravitational disturbances. That meant they must have existed before the sun gained mass enough to stir the cosmic cloud. Their structure showed that they had lived in an environment calm enough for crystals to grow layer by layer in steady patterns. Those slow patterns could never form in the later violent age of swirling dust, collapsing gas, and intense radiant heat. Only the deep quiet before the sun could allow such delicate structures to survive, and their presence proved that these bodies began their journey long before the first solar pulse spread across space. As the sun expanded into full strength, its wind pushed lighter particles outward, yet the oldest asteroids held their ground because they were dense enough to resist the early storms. They drifted into orbits that allowed them to survive instead of being thrown into the sun or cast into the cold void beyond. This endurance made them rare objects because many other early bodies were destroyed during the chaotic rise of the new star. Those that remained formed a small population of survivors who carried both the memory of their origin and the scars of the sun's early fury. With time, these asteroids became natural laboratories for understanding the formation of planets, because they showed what existed before any planet took shape. Their composition proved that the earliest building blocks were not uniform. Instead, the universe provided a mixture of metal silicates and carbon-rich matter. The diversity inside these ancient stones became the proof that planet formation did not follow a single pattern. Instead, it drew from a wide range of ingredients spread across the cosmic cloud. This insight changed how scientists understood the birth of planets, because it meant Earth and other worlds were built from materials that predated the sun itself. The oldest asteroids also revealed secrets about radioactivity in the primordial region. Some held isotopes that could only form in the life cycles of massive stars that lived far away from our forming system. The presence of those isotopes showed that explosions of powerful stars had seeded the cloud long before the sun emerged. This discovery allowed researchers to trace the cosmic ancestry of our system back to stellar events that occurred millions of years before the sun's first light. It also proved that our solar region was shaped by energies from distant parts of the galaxy, not just by the sun alone. Continued radiation from the new sun left deeper marks on the outer layers of these ancient stones. Over time, solar wind stripped away lighter elements and reshaped the chemical balance on their surfaces. This allowed scientists to measure how intense the early sun was during its youth. By comparing inner layers untouched by radiation with outer layers altered by solar storms, researchers built a timeline of solar activity stretching far back into deep cosmic history. Thus, the oldest asteroids became not only storytellers of the era before the sun, but also living records of the sun's earliest growth and transformation. Their slow movement through space also revealed how cosmic forces guided them across billions of years. Gentle pushes from sunlight, known as thermal drift, gradually shifted their positions through the solar zone. This slow migration explained how objects that formed far from the newborn sun eventually reached closer regions. These movements helped shape the environment where planets formed, because drifting bodies delivered rare minerals and organic compounds to growing worlds. Without those ancient travelers, Earth may not have received some of the materials that later helped support life. The oldest asteroids carried within them the signature of cosmic cooling, a process that affected their cores in different ways, depending on how large they were. Small bodies cooled quickly, leaving behind fine grain textures, while larger ones cooled slowly, producing layered structures. These differences provided a roadmap for understanding how size influences the evolution of early planetary ingredients. By studying these patterns, scientists learned how the earliest solid objects changed over time, and how some grew into protoplanets, while others remained small relics drifting alone. Many of these ancient bodies still orbit today in distant or stable regions because those areas offer shelter from violent gravitational forces. They remain untouched in deep space where time moves slowly and change is rare. Their survival across billions of years is a reminder that the oldest truths of our solar story are not found on planets shaped by heat and transformation, but on small silent stones that have kept their form since the beginning. These unbroken witnesses continue to reveal the past each time a sample returns to Earth or a spacecraft studies their surface up close. The oldest asteroids drift quietly through space, carrying a story older than the Sun itself. Every pre-solar grain embedded inside them preserves the memory of stars that died long before a solar system existed. These bodies are silent witnesses of a universe that existed before the dawn of our Sun and before planets had formed. They are cosmic time capsules traveling through the eons without losing their identity. Their endurance shows the resilience of matter and the persistence of history in stone. They are not merely fragments of rock. They are the beginning of a story that spans billions of years across the galaxy. Through their preservation, scientists have learned that the solar system did not emerge from a single point of creation, but from a complex mixture of ancient material from many stars. The grains inside these asteroids reveal processes from distant stellar furnaces, supernova explosions, and slow aging stars. They hold isotopic patterns and organic compounds that no planet has retained. The study of these stones connects us directly to events that occurred before sun shone. They are a bridge between interstellar history and the birth of the solar system. By understanding their composition, scientists reconstruct the environment that existed in the dark clouds before the sun ignited. These asteroids also reveal the violent and chaotic early history of the solar system. Collisions sweeping through the asteroid belt created rubble piles and layered fragments, yet the presolar grains survived intact. They endured the storms of radiation, the push of solar wind, and the gravitational dance of planets. Their survival demonstrates how ancient material can persist even in turbulent environments. In this way, there are lessons in endurance and records of cosmic resilience. Every fragment that reaches Earth as a meteorite is a messenger carrying billions of years of history from the edges of the solar system into our hands. Primitive meteorites brought to Earth by these asteroids have allowed scientists to study grains older than the Sun in laboratory conditions. Using precise isotopic analysis, they have identified materials formed in ancient red giants, supernova explosions, and other long-gone stars. Organic molecules preserved inside these meteorites provide clues to the ingredients of life that existed across the galaxy long before Earth formed. The ancient asteroids did more than preserve dust. They delivered history, chemical signatures, and building blocks across space, bridging interstellar epochs with the forming planets of the solar system. The oldest asteroids remain today in stable orbits in the asteroid belt and beyond. They serve as enduring witnesses to a universe before the sun. Each asteroid carries in its interior a record of cosmic events from before planetary formation and before the ignition of our star. They link the time of interstellar clouds with the birth of the solar system and offer a direct glimpse into the processes that shaped matter across billions of years. They are reminders that even the smallest and seemingly insignificant objects can hold the greatest truths about the origin of everything we see. As we study these ancient stones through meteorites and spacecraft missions, we continue to unlock the history of our cosmic neighborhood. We learn that our sun is young compared to the oldest solid matter it surrounds. We learn that our planets are built from material older than the central star. We understand that the story of the solar system begins long before its light first reached space, and that the tiniest grains preserved in asteroids can tell the greatest cosmic story. The oldest asteroids are timeless witnesses. They're the enduring memory of stars that once lived and died. They're the silent archivists of our galaxy. Through them we glimpse a universe where history is written not in words but in stone.